The story behind me being hired for my particular position, I'd actually been ranked number 3, and the person ranked number 1 is a very well-known Cyprus research. That's where the perceptions started. But the really economically significant VMS deposits are not in those terrains. Things were moving so fast scientifically before the work of people like to decide as to whether a given sulfide deposit is syngenetic or epigenetic, is genetic models can be developed and derived by people who don't know what the model should be. Do you mind if I answer that kind of off camera? My name is Ed Spooner, and I was a prof at the U of T from 1977. My last field trip that I ran at the U of T was in 2019. Before the U of T, I was from the UK. And if we talk about Cyprus work, the Cyprus work was actually done while I was in the UK instead of while I was here.
Publication was in 1977.
Was in 77.
When you had joined the department.
Same year, exactly. Yeah.
So University of Toronto Economic Geology department was a fairly sort of heavyweight at the time when I was here as a student in the 80s and 90s. When did that economic geology unit come together as a powerhouse?
In particular, that would have been in the 1970s.
Okay.
Already there were two really exceptional people, Frank Beals, on carbonates in general, and then leading from carbonates into sediment-hosted lead zinc in particular. And then Frank was joined by an exceptional geochemist by the name of Greg Anderson. And the two of those and their research group did fantastic work, in particular on MVT deposits. Then, and that was probably in the early 70s, Tony Noldrit joined the department, and Tony's field was in orthomagmatic nickel, copper, platinum group element deposits. And Tony was phenomenal as well. And then Steve Scott would have joined the department mid-70s, thereabouts. Steve, likewise, was tremendous. Those were in mineral deposits, but there were other geologists on the staff who were excellent in their fields. For example, in structural geology, there was your supervisor, Fritz Werner, who was tremendous, and an older guy called Jack Curry, who was very solid. So it was even in micropaleontology, there was Jeff Norris, a world-renowned figure. So yes, it was strong in economic geology, but one of the things I think that made it really good, it was strong in a lot of geology altogether.
So tell us your story about how you were hired at the department. You're telling me about that.
Okay, so the story behind me being hired for my particular position, and I started in the August of 1977. It starts with a mineral deposits geologist by the name of Steve Kessler. And Steve wanted to return to the US, which he did, and so then a position came available. I was passing through Toronto in 76, visiting a couple of grad students who were here at the time, who'd come from the UK, James MacDonald and John Thompson. And right in King's College Circle, we met up. There was a big celebration there at that time. And Tony asked if I might be interested in applying, which I was in need of a job and coming up. And so, of course, I said yes. And then quite a few years later, I learned the history behind what happened. And that was that I'd actually been ranked number 3. And the person ranked number 1 is a very well-known mineral deposits geologist called Dick Silito. And the rumor was that Dick was lost on a job somewhere in the Korean Peninsula and was not responding to letters, telexes, or anything like that. And so it was taken that Dick was not interested in this particular academic position. Rank number 2 would be of great interest to people in Australia because the number 2 guy was Ross Lodge, who then returned to Tasmania and was leader of the mineral deposits group there at the University of Tasmania for 20 years, maybe, something like that, and built up its reputation as being one of the best places in the world. Okay, well, Ross was ranked number 2. I was still number 3. Apparently, the feeling amongst the people on the panel was that Ross's research and Steve Scott's research were too close together. They were both extremely competitive people, and it was just reckoned that that was a clash that's probably worth avoiding. And there was total confidence that Ross Lodge would find his way in the world very well anyway, which of course he did. So then it came to me, and yes, I had research interests that connected with Steve's, but I had other research interests and I was fairly adaptable. And in fact, Steve and I got along very, very well for all the years until he passed away.
If you can explain the history of the use of fluid inclusions to find out the environment of deposition and how significant your work was at Cyprus.
So we used fluid inclusion research from one particular deposit in the seafloor rocks, Cretaceous seafloor rocks of Cyprus, to constrain the depositional temperature, which was in the low 300 Celsius, and in particular, the bulk composition of the fluid, which carried the iron, sulfur, and copper, principally. Now, I was led to that because I'd worked on ophiolitic rocks for my undergrad thesis in Greece, and then the start of my PhD in northern Italy, and had realized that there was pre-tectonic emplacement hydrothermal alteration of the high-level rocks. I was very familiar with hydrothermal alteration because before going to university, I'd worked underground as a sampler in southwest England. So yeah, I was familiar there. The rocks in northern Italy were too deformed to get very far genetically. So I started reading about Cyprus, and it had already been thought that the massive sulfide ore related to the pillow lavas in Cyprus was formed on the seafloor, but people didn't know how. Okay, that had been done. What I was interested in doing was trying to find out the characteristics of the hydrothermal fluid itself. And I came across a paper by Trenery and Pocock describing a mine in western Cyprus called the Limni mine, which in Roman times had been mined for altered massive ore, but in the 1970s, it was actually the underlying feeder zone, the stockwork, that was being mined at about 1%, 0.8 to 1% copper. The seafloor rocks of Cyprus have a very, very, very low, essentially no internal deformation, just a very weak, large open fold. So I reckoned I was in with a chance to find fluids related to the mineralization. So I went to Cyprus in 75, shortly after the end of Turkish-Greek hostilities, and mapped and sampled the Limni mine, took the samples back to Oxford. I'd already managed to persuade Prof. Vincent in Oxford to buy a really good heating and cooling stage to do the measurements from a group at the University of Nancy in France. So great thanks to Prof. Vincent there. It needed calibrating, And somebody who actually still works at the U of T, called Colin Bray, he had just started a PhD in Oxford under my supervision back in Cornwall. And Colin actually calibrated that stage, which is why the paper is Spooner and Bray, because it needed calibrating. Colin Bray did that. That was central to the research. Fluid inclusions are trapped samples of fluid, usually with a little bit of vapor. Sometimes fluid inclusions can be almost entirely vapor if they formed from a vapor, and they were trapped inside minerals. So for one to be able to make measurements on them, they have to be in a transparent mineral. And one of the best, not the only, but one of the best, of course, common transparent mineral is quartz. A whole bit of observational research then has to be done, because the key question is, were the inclusions that you find, if you find them, were they trapped while the quartz crystal was growing? So therefore they would then be relevant to the growth, the transport and growth of the quartz and other associated minerals, or are they in cross-cutting curved planes? So then they are secondary, and they were introduced at any time after deposition. And so their significance is open to question. The key information that you can get from inclusions at low temperatures, so this is dropping the temperature using liquid nitrogen. You need to drop the temperature really low to get the inclusion water to flash freeze. Then, in a controlled way on the stage, you observe the inclusion. Almost all natural fluids have dissolved salts, as well as the H2O. So they then have quite a long temperature interval where there's coexisting ice and water. So you focus on the ice. The measurement you want to make is the temperature at which the last ice crystal disappears. On large inclusions, you can see that, so you can measure it. Small inclusions, there's uncertainty. But you know if you've got it right, because if after you think the last ice crystal has disappeared, you quickly drop the temperature, if the ice regrows, it means there was still a nucleus. If, on the other hand, you drop 10 degrees, nothing happens, it means that the last ice crystal has gone and you've done the measurement. And you can then use that temperature measurement to convert to, normally, it's equivalent weight percent NaCl, which is the amount of dissolved sodium chloride, which would produce the drop in temperature you've measured. And that's a general guide to salinity. Natural fluids vary in salinity from close to zero in some high-level subaerial epithermal gold systems where meteoric rainwater is present at high levels, right the way to saturation in NaCl, which is 20-something%. Even with, say, if it's a calcium chloride-rich brine, then it goes to even lower temperatures. So it's a general measurement of salinity. So common or garden seawater has a salinity of 3.23 weight percent, and its ice crystal disappearance temperature is minus 1.9 Celsius. That's that type of measurement. Going up temperature, much easier measurement. You measure the temperature at which, let me backtrack. Okay, when an aqueous inclusion is trapped, it is trapped as a single phase. Then it cools down naturally. The host crystal doesn't change its dimensions that much. The liquid, on the other hand, shrinks significantly, and a vapor bubble forms. So then at room temperature, you see liquid plus vapor. The usefulness of the stage is then going up temperature, and you measure the temperature at which the vapor bubble disappears. That's what you record. That's a fun measurement to make, because as the bubble gets smaller and smaller, it goes into what's called Brownian motion, which is the statistical inequality of atoms, molecules colliding with the bubble. Starts to zing all over the place, and then suddenly is gone. And you have a little thing that you press, you record the temperature. I won't go into details about how you determine whether that temperature is a depositional temperature or whether it requires a little bit of temperature to be added. It's not really relevant to Cyprus, because the depth at which the Cyprus deposits formed corresponds to a relatively low pressure. So there would have been a pressure correction needed, but it's not much. And the typical temperatures that we got were between 300 and 340 Celsius, thereabouts. Now, that paper was published in Nature in 1977, and I think it was also in 1977 that the first records of dredged sulfides, and of all places, they were published actually in National Geographic magazine. And these were the expeditions led by Bob Ballard. And National Geographic had put up the money, so National Geographic got the rights to releasing this information. And it just totally blew people away. And I haven't had time to check that, but I'm pretty sure that was also in about 1977. And then things took off. Going back a little bit and talking about other most unusual people, where I started my PhD at the University of Manchester, there was a really unusual New Zealand geophysicist by the name of John Elder. And John Elder gave us lectures on the dynamics, thermodynamics, circulation mechanisms and controls of the geothermal systems in the North Island of New Zealand. And it was from John Elder that I learned about geothermal systems and their behavior. But they were subaerial, so they had big zones of recirculation. But I'd like to thank John very, very sincerely for that. But I was, of course, well aware that we were dealing with the seafloor situation, so I thought logically this is now an open upper interface, and so there's nothing really to constrain the discharge of fluids coming straight out. There'll be a very limited recirculation zone. And so that was the hypothesis I was interested in testing, was whether or not the Cyprus sulfide deposits could have been produced by geothermal circulation within the seafloor, activated by high-level melts, because below the pillow lava and sheeted dike levels in Cyprus, there is a very, very well-defined composite gabbro layer, which of course corresponds to igneous liquid heat sources.
Were there any other competing hypotheses, the explanation of the Cyprus deposits?
What were people thinking about the origin of fluids related to the Cyprus deposits? And I think my reply would be that things were moving so fast scientifically before the work of people like Beer for the Cyprus Geological Survey and Kokos Konstantinou, also for the survey. There'd been really not much thought given to the origin of the fluids in the ophiolitic rocks. The main emphasis had been on determining where the deposits were, their size, their controls, to support the minerals industry of Cyprus and the taxation income that it would generate. The word that I remember from the folk who wrote about it at that time was an old English word called emanation. That was as far as they got. They had not had the advantage of someone like John Elder talking about how fluids can convectively circulate in the shallow crust in response to high-level igneous heat sources. So, yeah, thinking back on it, listening to John, it's one of the most important things that ever happened to me, actually. Yeah.
Mhm.
And so then when myself and Colin started the research, there was actually not much prior thought. And likewise, there was essentially zero prior thought about mineralization on the actual seafloor because that had not been discovered. That was not discovered until Bob Ballard's expeditions, published in National Geographic in 1977. And that started off just with some dredging of some sulfide fragments.
So that came after your paper, or around about the same time, or?
The results of finding evidence for hydrothermal activity on the seafloor at actively spreading ridges, the timing for that finding, how did that compare with the timing of our research on Cyprus? And I would have to say at this point, basically, it was the same timing, especially if you consider, you need a lead time to go and do the research in Cyprus. You need a lead time before going out in a ship. So I would say pretty much the exact, very, very closely similar time, but with essentially no communication between the two groups. Yeah. And I'm starting to remember a bit more. There was a French expedition on a spreading ridge off Mexico, and the French, they must have had a submersible or a submarine camera because there are drawings of the sulfides that they encountered there. And that paper was published in Nature, and that would have been published in 76, 77. And then it was very shortly after that, I think maybe on the same ridge, that they actually found the first active discharge of high temperatures. Of course, they didn't have a clue how high the temperatures were. They put an old thermometer in a plastic housing in some of the discharged fluid, and of course it melted in front of their eyes. But they still had no conception that the temperature could be 200, 250, 300 Celsius. And that even remained true when Alvin actually dived on one of these, and Alvin had a thermocouple. And before they actually determined a temperature of 300 thereabouts, they let Alvin, and Alvin had windows, but the Alvin windows were thick, transparent plastic. And they actually let Alvin get quite close to these 250, 300 degrees centigrade temperatures before they realized how hot they were. So yes, there was a lot of it was a very exciting time.
Is okay. The Cyprus fluid inclusion showed, seawater involvement. What I want to know is, after the discovery of all these sulfides on the seafloor, the idea caught on that the sulfides that are seen on the ground, like, the Rio Tinto and so forth, were considered to be ancient equivalents of these seafloor massive sulfides. It caught on eventually that almost every sulfide deposit, terrestrial sulfide deposit, became an ancient syngenetic deposit. Is that pretty much the way it evolved?
Yes.
What I want to know, I guess, is the question is, how fast did that sort of take up, or this idea of ancient massive sulfide deposits being possibly syngenetic? Because right now, virtually anything that's sulfide that's found in ancient rocks are considered
in ancient volcanics.
Ancient volcanic, yeah. So
yes,
I want to know how that sort of evolved over time.
Okay, the sulfide deposits in Cyprus and also Oman, and other places too, were contained within ophiolitic sequences. In particular, the presence of the 100% sheeted dikes, which even contain dikes which have intruded dikes, so you get a series of asymmetric chilled margins. wherever that spreading process may have occurred, whether it's at a ridge, whether it's a ridge behind an arc, don't think that matters too much. That's where the perceptions started. But the really economically significant VMS deposits are not in those terrains. They are in the historically significant, for example, Rio Tinto district of southern Spain and Portugal, the Curacao district, and then there are metamorphosed equivalents going up to really, really high metamorphic grades, maybe like the Broken Hill deposit in Australia, and many, many other deposits throughout the world, particularly, for example, here in Canada, like the huge Kidd Creek deposit, the deposits in Noranda, including the Horn deposit. The Horn deposit would have been in production since at least the 1930s. Kidd Creek, I think, was discovered in the 1960s. Now, the associated igneous rocks here are mafic, but very, very strongly also intermediate to felsic. And the research on the geochemistry and the sequence and arrangements is that these deposits formed in, loosely speaking, some type of, well, certainly speaking about the Phanerozoic ones, those formed since 600 million in a submarine arc setting, not a seafloor spreading setting. So to give you an idea of the type of setting I'm talking about, if you come down through Japan, then Japan is, of course, subaerial. But as you go southwest from Japan or due south from Japan, the island arcs continue, but the island arcs are submarine. If you go to the Caribbean and you go down to the island of Grenada, okay, Grenada is subaerial. But just to the northwest of Grenada is a submarine volcano, the name of which just escapes me, which erupts periodically in the submarine environment. Now, that is the general environment in which these deposits are thought to have formed. So there were researchers, for example, my colleague Steve Scott. When I was appointed at the U of T, Steve was actually in Japan doing research on the Curacao deposits, which are very young, Miocene in age, in north-central Honshu. And Steve and his co-workers in Japan and elsewhere were very happy that the massive ore in them was formed on that seafloor at the time. And they had stockworks underneath them, and they were often positioned on the sides of submarine dacite domes. My guess is that that evidence is hopefully not too bad. As I said, Steve was in Japan at the time I was interviewed. So Steve and a small number of other people just took off with that idea at that time, building, and literally in the space of just a few years, it just became the model, rightly or wrongly, it just became the model that what were called VMS deposits, pretty much regardless of location and age, it just became the standard model. Was there much really rigorous research then done to be sure that, for example, they were asymmetric? In other words, with a feeder zone underneath, but not a feeder zone on top? Yes, there was some of that research. I remember a deposit that was looked at carefully, maybe by Harold Gibson and others, in the Noranda camp, called the Millenbach deposit. Millenbach was really interesting because it had two massive sulfide lenses. The top lens was asymmetric. It had a feeder zone underneath it, not a feeder zone on top. But then the mining people had followed that feeder zone, and actually it emanated from a mineable massive sulfide deposits underneath it, then the feeder zone continued to depth. So I would say in a matter of just a few years, it became the standard model. Necessarily, does it really apply truthfully to every single deposit that's called a VMS? I think one would have to say that one's not necessarily sure of that. I think that would be the honest answer.
Leading from that, there were many massive sulfide deposits known before this revolution happened. But now the USGS has a list of all the VMS deposits. And if it's a sulfide deposit that has volcanic type rocks nearby, doesn't have to be hosted in volcanics, it just is automatically classified as a VMS. So without even investigation, that's what really
Yes.
worries me. But anyway,
Yes.
that's just a comment. But
No, it's a very interesting and important point that genetic models can be developed and derived by people who don't know what the model should be. So they look at the rocks as closely as they are capable, or they should do, and analyzing the features in the rocks as much as possible, and then maybe a model is derived. When that has happened, then maybe people's critical faculties are turned down a little bit. And really, that's not necessarily a good thing. So there's a question about the significance of fluid inclusion salinities with regard to whether or not a deposit is truly syngenetic. In other words, it formed while the sequence that contains it was forming as part of that sequence, or epigenetic, meaning that it is later than that sequence and deposited 1 year later or 600 million years later. I think my answer to that question would be that fluid inclusion, salinities, and temperatures themselves, they tell you about the fluid. I don't think that they can tell you about whether a deposit is syngenetic or epigenetic. I think the evidence for syngenesis or epigenesis, the evidence there is structural and textural. Zoning can come into play, but I would say that that's essentially backup. Zoning, the type of zoning I would be talking about with VMS deposits, are from higher temperature, deeper zones with strong copper, maybe gold contents, zoned out to lower temperature zones, lead and zinc, and silver rich. So that'd be my response to that. The key. So what you have to do to decide as to whether a given sulfide deposit is syngenetic or epigenetic is map it extremely carefully and also look at the alteration state of the hanging wall and of the footwall, if you know which is which you may not. And also look at the depositional textures, both more like structures on the scale of 0.5 meter to 1 meter, right down to what you can see in the microscope.
Yeah, it's really interesting answer. Like I didn't expect that. So how about isotopic evidence that people talk about?
When you start adding in other geochemical evidence, how can that affect things? Again, my reply to that would be that the first thing to establish with a high degree of confidence using the structural and textural information is whether or not what you're dealing with has a high probability of being syngenetic or epigenetic. Then once you've done that, then you can apply geochemistry to try to find out more about the origins of fluids, the temperatures of fluids. So one of the significant findings for the VMS deposits that formed in submarine arcs is that there is quite good evidence in some cases that there is, of course, a magmatic vapor component in the fluids, which is hardly surprising. Anyone who has either witnessed or seen on film the eruption of a classic calc-alkaline volcano, for example, in New Zealand, in Indonesia, one of the ones I'm most familiar with right now is Montserrat. Just the sheer power and volume and amount of magmatic volatiles, which are about typically 60, 70, 80% H2O, but then 20, 30% CO2, and then a string of other volatiles, significant argon concentrations, for example. One of the most important diagnostics of fluids, for example, discharged, say, from Montserrat, is the CO2 content, 20 to 30%. Then a question that can be asked is, when you have inclusions formed at depth, so high pressures, can you see that CO2 or not? And the answer to that is yes. And a classic example of that, there are many, but a relatively early classic example, two classic examples from research done at the University of Toronto by Ann Thomas on the Tanko lithium-rich pegmatite in southeast Manitoba, and then for his master's thesis by Dave Burrows on the Mink Lake molybdenum deposit in northwest Ontario. In both those cases, large amounts of liquid CO2 in three-phase, liquid water, liquid CO2, vapor inclusions can be seen in primary inclusions. And that actually was a factor which led me and my group, with varying degrees of how voluntary they were, to an interpretation for gold quartz veins, for example, in Archean and Proterozoic terrains. And that's a big discussion and argument which can wait for another day.
That is a big discussion. Yes.
But I was thinking back.
Yes.
And in terms of our research sequence, we'd started off in central BC, James McDonald's molybdenite deposit, right around a high-level stock, full of CO2-rich inclusions. Okay, then we went up to the Yukon. Then Anne did her amazing research on the Tanko pegmatite. But that's a different kind of composition, so I didn't really count that. But then I started Dave on his Mink Lake molybdenite deposit. And again, CO2-rich fluids. And that's actually what led me into Archean gold systems when I found out how many of them, particularly Ontario, Quebec, had very high concentrations of mineable tungsten. And in the Kirkland Lake, I don't think it was ever mined, but significant amounts of molybdenite. I thought, hey, what are these metals doing in a gold system?
Actually, very interesting that you say that you check the structures first, because that's not the impression that I get of a lot of the research, VMS research. They ignore the structures. They just assume that this is a deformed syngenetic deposit, and they go on to talk about geochemical composition arguments, basically. So obviously, if you can just ignore the structural evidence and then just ram home with the geochemical argument, then you're basically missing out on half or majority of the evidence. I mean,
Absolutely.
to do the workflow would be to do the mapping, work out the structural relationship first, then do the geochemistry.
Yes. What kind of a research work sequence is likely to come through with an interpretation that's as close as possible to the correct interpretation? And here I go back to my earliest experience, which was working as a sampler and underground mapper out of secondary school before I went to university, where I worked for several months as a sampler in the underground evaluation phase of a tin mine in southwest England that went to production. And it was there that the geologist in charge disciplined me into making a whole set of observations, anything relevant. If there was a mineral vein, measure the geometry. If there was a textural sequence showing that minerals were deposited in any particular sequence, note it. Just note everything. Don't think, observe, and note. And I would say that's a pretty good guide into a good start. When it comes to structural geology, I would point to Fried Schwertner here in illuminating to me and general reading just how important quantitative, careful structural analysis of brittle structures and ductile structures essentially always is. Now, you don't know how important it's going to be down the road, but you just do it, and then you find out.
What I found interesting with your papers that has a lot of data, like observational data, which is not not necessarily the usual way that people do things. They sort of even start out with the model, talking about the model. You know, they kind of assume that the model applies, and they kind of fit in their observations to the model rather than the other way around, which is, as you say, take a lot of observations, because that basically is the information that's going to stand the test of time. So it'll be nice if you can actually sort of tell everyone that, because we both agree on that point, I hope. It's
Without a shadow of doubt.
Yes. So that is, to me, that is a really important point to emphasize, because I do somewhat, I don't really like the model-driven papers at all. Like I find them really quite.
If you assume a model before you start, then what's it going to tell you?
Yeah, absolutely. So yeah, it's one of the most basic geological things. I mean, you know, university professors always tell you, separate your observation from your interpretation.
Absolutely.
That is absolutely critical. And this is not something that is routinely done, unfortunately.
So from what I'm hearing about the way that geological and earth sciences university education may have evolved in recent years, is that separating the different categories of observation, structural, textural, mineralogical, etc., from the interpretation of what has been observed. The distinction between those two may have been eroded somewhat. And I would say, based on my experience in geology going back to 1968, and involved in quite a lot of practical geology and also in research geology on important types of deposits, is that it's critically important for young people to be taught what to observe, how to measure it, and to be absolutely sure to do that first. The discipline of these detailed observations will help young people very much in the work environment, because they will be required to examine split core, for example, on any drilling project that they're involved with. They'll be required to describe outcrops if it's at a mapping stage. So it's the key part of the discipline. Interpretation can come later.
What are the consequences of this backwards method of measurement and observation? Like, what will happen in the world if we continue to go this way?
Model driven.
Yeah. Like, what are the consequences of that on a large scale?
Do you mind if I answer that kind of off camera?
Yeah. Why is that?
I mean, partly because I've never thought about that very much. So really am just thinking aloud. I just think it leads to a lack of competence.
Mhm.
Where you have a lack of competence, then you have a lack of effectiveness.
Mhm.
So then you translate that into the real world of mineral companies. And I would like to think that those companies, like Agnico Eagle, for example, which do support and require good quality observational work, that they will be more successful, economically successful on behalf of their employees and shareholders than companies which don't have that discipline. I can say some words about a really fascinating project that I was involved with, where, again, it was another case, like VMS was before, where it was a new type of mineralization. So it was absolutely not understood, and how the deposits formed was not understood when we started. And that was on the famous unconformity-related uranium deposits of North Saskatchewan. I was interested in uranium because I was interested, even at that, I'd read The Limits to Growth. So I was already interested in what the power sources were going to be to replace hydrocarbons. Uranium and fission reactors was obvious. And then here were these incredible, crazy high-grade uranium deposits in North Saskatchewan turned up, and they'd never been seen before. So that was Colin Bray's postdoc, was looking at McLean Lake. So that was a fascinating exercise in working up from detailed observations on the core. There was no outcrop. Working out a depositional sequence. And then once that was worked out, then using that as a control for, in particular, isotopic analysis. Yeah, fascinating.
I think that's pretty much wraps it up. The gold story would have to come another time because that's a completely larger subject, because you spent
It's huge.
most of the
It's huge.
time on that particular subject in your research in gold.
Well, it was really, really big, 80s and 90s.
Yeah.
Yeah. But I was always getting involved in other projects because I always knew that the main thrust would only last so long. I just got interested in other stuff. So, off I went to North Saskatchewan.
All right. Yeah. Thanks very much, Ed. Appreciate it.
You're very welcome, John.
Yeah.
You're very welcome.
Really appreciate you coming out.
Oh, one more clap, actually.
Yeah, one more clap before we turn it off.